everyone. My name is Roi Lipman, and I am working as a software architect at AVG. For those of you who don't know AVG, it is a security company which has evolved into a peace of mind company, serving over 100 million and 50 users worldwide, providing products in the security, performance, and privacy. Today, I would like to talk to you a little bit about passwords. So, unfortunately, these are the top most common passwords for 2012. And it's pretty obvious that these passwords are pretty weak. With that, I would like to talk a little bit about password properties. What makes a password strong? So the first property is the key space or character set that a password is using. So for instance, a password which uses the digit key space would have only 10 possibilities per character. On the other hand, a password which will be using every possible character within the standard keyboard would have 94 possibilities per character. Next up is the length of the password. So we can see that the password using 8 characters within the digit key space would have 100 million possibilities. So this might be considered as a big number, but it really isn't. And as you can see, as we go further, as the password length increases, the number of possibilities increases. Also, if a password is using a wider key space, also the number of possibilities increases. And as we go to the bottom right corner of this table, the number of possibilities increase dramatically. These numbers are enormous. It's really hard to wrap your mind around how big these numbers really are. So suppose you're asked to create some kind of a computer system where authentication is required. So your users would have to give their credentials in order to use the software. Most likely you would want to use some sort of a database to store your user credentials for them to log in. So you might create some sort of a form similar to this one. So a user wishes to use your service would have to provide his username and password. Now, upon registering, a new record is about to be added to your database. But because databases can be compromised, it would be considered as a bad practice to store your user's password as plain text. So what most developers would do, they would store a hashed value of their user's password. So upon signing up, a new record will be added to the database. You can see that the username is stored as plain text, but the password is hashed. In this way, no one, including the authentication method, will be able to know what was the actual user password. So a login process would have to take the user's password and rehash it, comparing the two hash values for that particular user, and in case of a match, the user is authenticated. So a little bit about hash functions. I've decided to demo the MD5 because it's one of the most popular hash functions out there, but there are several more like the NTLM and the SHA-1, all of which have the same properties. So the first one is hash functions are one-directional, meaning that you can't reverse the process. You can't go from the hash value back to the given input which hashes to that particular hash. If you know otherwise, please come and talk to me. The second one is that all hash functions have a fixed output length, meaning that it doesn't matter how long is your input, you're always going to get the same output in length. They're easy to compute. It shouldn't take too much time to calculate a hash. There's collision resistance, meaning that it would be really hard to find two values which will hash into the same value, into the same hash value. Pre-image resistance, meaning that for a given hash it will be hard to find an input which will result in the same hash. And the other way back is that for a given value it would be hard to find another value which will be hashed into the same hash value. Okay, so suppose that an attacker has somehow managed to get their hands on your database. They can't, as I said, they can't use the hash values in order to get access into your system. So an attacker would have to do some kind of cracking in order to realize what value was put in order to get the hash. So an attacker would probably have a couple of options. One of them is brute force. A brute force attack means that an attacker will use every possibility within a given key space or password length, and he would just use all possibilities in order to find the right input for a given hash. Another attack vector is the dictionary attack, which is pretty similar to brute force attack, only that the search space is much smaller. For example, an attacker would try to take every word within the English dictionary and hash each word. And the last one is rainbow tables, which are simply a database of pre-computed hash where one can take a hash value and just look it up and see what value was used for that particular hash. So in my talk, I would like to focus on brute force attacks. So in this graph, we can see how much time would it take an attacker to crack a hash for every key space and for any password length within the range of 6 and 12. We can see that for the mixed alpha digit key space, a password of 9 characters will take about 10 years with a general CPU. So we can use CPUs to calculate hashes. We can see that on a high-end CPU, we can calculate about just over about 250 million hashes every second. So up until now, I haven't mentioned GPUs. I would like to give a short introduction into GPUs because the main idea behind my talk is to use GPUs for password cracking. So we're going to talk a little bit about GPUs, and we start with how much time would it take a GPU to crack a password. So on a mid-high range GPU, we're able to crack just over about 1 billion hashes per second. I would like to give a quick review of the architecture of the CPU against the architecture of the GPU. So on a modern CPU, you would have just a small number of cores. Here we can see a CPU with 4 cores. Each core has 2 levels of memory cache, the L1 cache and the L2. All cores have access to the L3 cache, and all cores have access to global memory. On the other hand, the GPU has lots and lots of cores. If I could, this slide will stretch all the way back to the end of the room. Each block of cores has its own access to a private shared memory, and all cores are able to access global memory. Now, this is not the same global memory as we've seen in the slide before. This is the GPU memory. Up until today, the GPU is unable to access the CPU memory and vice versa. So the key differences between CPUs and GPUs. The GPUs has lots of, I would say, slow processors compared to the CPU, which has only a few, but they're much quicker. The GPU has a simpler hardware control, which allows for physically more space to pack in more cores. GPUs do not intend to be backward compatible. When it comes to hardware, backward compatibility is achieved by the driver. On the other hand, CPUs are backward compatible. You should be fine running code you have compiled about 10 years ago on a modern GPU. Again, the GPU has a large number of cores, and the GPU is optimized for throughput while the CPU is optimized for latency. So just to make clear what's the difference between latency and throughput. Suppose that the Ford factory is able to manufacture a single car every 10 minutes. So that is pretty impressive, that's pretty quick, and that's the idea behind latency, to minimize the time it takes to compute a single instruction. On the other hand, suppose that the BMW factory is able to manufacture a single car every 30 minutes, but BMW has a large assembly line which allows them to manufacture 10 cars simultaneously. So that's the idea behind throughput, and that's what the GPU is trying to achieve. It tries to maximize the amount of work, to maximize the amount of computation it can do per unit of time. So this is the most modern GPU I could find on NVIDIA's page. It has 2300 cores. It runs at the clock rate of 900 Hertz, and it got about 3 GB of memory. So I think this is pretty impressive. Okay, so in order to take advantage of the massive computational power the GPU has to offer due to its massive amount of cores, one has to think about a new programming paradigm, which is called parallel programming. The idea behind it is that your code, which will be executed on the GPU, is going to run on hundreds of thousands of simultaneously running threads. And this requires a different mindset when it comes to programming. You should definitely think about trying to migrate your application into to be using GPUs, but you should know that not every problem you will encounter is fit into GPUs. Good problems are ones which can be broken down into many smaller instances, which can be solved individually, and then you will have to recombine each solution to have a complete solution. So an example of such a problem would be matrix addition. The ones of you who have taken linear algebra courses will be familiar with it. Basically, you have two matrices which you want to add. So here we can see matrix A and matrix B, and we're going to do a summation. So on the CPU in the serial world, you will probably use two for loops, one going over each of the matrix rows and another loop which will scan the matrix column. And in each iteration, you are going to calculate a single element. On the parallel world, you would have many threads, each one responsible for a single element within the matrix. So I'd like to give a quick demo of the example just shown. So this code uses both the CPU and the GPU to do matrix addition. So let's just debug it. All right, this is our main function. At the particular time, we're still running on the CPU. We're allocating enough space for 3 5x5 matrices. This for loop is responsible for initializing the matrices. So let's have a quick look on which matrices were generated. All right, so we have our matrix A and matrix B. And now, as I've mentioned before, we know that the GPU can't access the CPU memory, so we're going to have to copy the matrices from the CPU memory back into the GPU memory. And now we're ready for the actual addition. So we're about to launch 25 threads on the GPU. Each one is going to be responsible for a single matrix element. So this is done. And now, in order to print the result, we're going to have to copy the result from the GPU memory back into our CPU memory and print out the matrix. So let's do a quick check. I'm looking at the first element, which is 6, and the first element in matrix B, which is 6, which should give us 12. And indeed, it seems to work. I just want to have a quick look on the actual code ran on the GPU, the add method. So this method gets to run 25 times on 25 different threads. Sorry about that. On the GPU, each thread is responsible for resolving its element index. So once he has its index ready, he could do the actual computation. Right, so up until the introduction of CUDA or OpenCL, programming to the GPU was not that simple. People would have to hack or to know GPU assembly, but people figure out that there's a lot of potential within GPUs, so NVIDIA came up with CUDA, which is basically a parallel programming platform. I've been using C++, so CUDA is also an extension to C++. It allows us to write code which will run both on the CPU and the GPU. Parts of code which are executed on the GPU are referred to as CUDA kernels, and CUDA is a multi-platform, so you can run it on Linux, you can use it on Mac or PC, and there's a variety of GPUs which will be CUDA enabled. I should say that other languages do support CUDA. You can use CUDA on Python, on Java, and I think also on .NET. So with that, let's get back a little bit to talk about password cracking. So if you remember, I was talking about an attacker who has somehow managed to get their hands on your database, and we've already seen that there's a lot of benefit and a lot of more computational power to GPUs, so it would be obvious to try and crack password on GPUs. So for my demo, I would like to show an application which uses both the CPU and the GPU in order to crack an 8 characters in length password from the alphanumeric key space. So just to do a quick math, the number of possibilities for such a password is 62 raised to the power of 8, which is just a huge number. So on a regular CPU, you will be able to crack about 150 million hashes per second, which is going to take us about 17 days to crack at the most. On the other hand, if we will be using GPU, we can crack 1,080 million passwords per second, so that reduces us to only 2 days of cracking. And the last line shows that you can use more than one GPU to work simultaneously. So the bottom line represents 4 GPUs working together in order to crack, and that gives us it will take us about half a day to crack the password. Right, so I've launched an application which uses both the CPU and the GPU, and it tries to crack an MD5 hash. It's supposed that this hash was created by a password of length of 8 and from the alphanumeric key space. We can see that my CPU has 4 cores, each one cracking at the rate of about, I say, 35 million hashes per second, and my GPU is cracking down at 153 hashes per second, give us a total of 328 hashes per second. So a rough estimation would give us about a week at the most to crack this password. So how can we improve? How can we make our database more secure? How can we store password more securely? Well, first, I would advise using salt. Salt is just a string which gets prepended or appended to your user's password, and the idea behind salt is just to extend the the search space. Salt was introduced also to encounter the rainbow table. If you have any question about salt and rainbow tables, please feel free to contact me after the talk. You could apply additional hash iterations, so don't run your user's password only once through MD5, but you can add additional rounds of hashing. And lastly, you could use more than one single hash function. Again, this will add more time to the cracking process, because some hashing function algorithms are slower to perform than others. So you could spice up your hashing function by, let's say, you're taking your user's password, you're adding salt to it, you're running through MD5 100 times, and on top of that, you're adding 10 times SHA-1. So I would like to advise you to try CUDA and to experiment with GPU programming, and try to construct a more secure database for storing your user's password. So if anyone has any questions, yeah, sure.
So using a very expensive machine for high-end graphic card, it will take you about half a day to crack, to reverse hash a hash password. That's what I saw in your slide. In about half a day, we can find one of many infinite possibilities that hash represents.
That's right.
But let's assume that the one you find is the actual password. And you were talking about a scenario where a database was compromised.
Mm-hmm.
Let's say your database has 1,000 users or 100,000 users. Okay, that means that within a year you'll only be cracking 750 passwords, right?
No, that's not correct, because you can crack more than one hash simultaneously, because
you need one machine per...
No, I don't. You could, for example, the application which I ran, I can give it a set of hashes, and what this program actually does, it goes through its search space, takes, for instance, the string A, hashes it, takes that hash and compares it against the hash list. Once it's found...
Does that work with salted hashes? Salted passwords?
For a salted password, you're going to have to, for every given input, you're going to have to try every salt you want to consider. Which could be anything. Right.
Prevents you from doing what you said. So you need half a day of a very expensive machine to crack one password, which means about 700 and something passwords a year, which means that you wouldn't get very far cracking any considerable amount of the database within years.
I would have to disagree, because we've seen database for big companies which were compromised, and a lot of hashes were cracked pretty fast. Now, not only that, you don't have to put a lot of money in order to create such a cracking box. There are online cloud services which will allow you to rent computational power. For instance, you could use the Amazon EC2 to rent a GPU cluster and run your attack from there. Yeah.
One thing you can also do is still use dictionary text, but with mutations.
Right.
Mutations, and that can greatly speed up and cover large quantities of. Even if it's a database of 100,000 users, you can easily get a large portion out of it because a lot of people, even though they may not use a dictionary word, they use one with a very small. I don't know if you know what Hamiltonian distance is, very small distance to an actual word. So you can really go and get a lot of passwords really fast. So there's actually no excuse not to use proper functions like, I don't know, bcrypt, scrypt, bk, pf2, etc. So honestly, because my opinion is that you don't have any excuse to not use those functions if you store passwords.
Right. Thank you. Okay. Thank you.